Hey everyone, good evening. Welcome to week 2, Music 499C SuperCollider. All right, let me make a little sound. Let's do a quick sound check. In OBS, I turned my mic and the signal coming from SuperCollider up by, I think, 3 dB each. So let me know if you can hear me and if it's an okay level. And here's some pink noise. Cool, thank you, Shwedi. Thanks, Tutmaich. All right, so here's the plan for today. I want to start by covering a few short items, some of which came up over the course of last week, just to clarify some of those things, and then we'll get into the actual meat and potatoes of week 2. We'll see how much we can get through. I'm going to try to stop right at 9:30, give or take a few minutes, so that I can take a few questions from everybody. So, see, just to go over brief things I want to talk about today. First item, envelopes and what are called done actions. I also want to talk about randomness in SuperCollider. We've been doing a little bit of randomness with rrand and xprand, but I just want to clarify a few things. And then we're going to get into all about arrays, which we also have been using, but there's a lot more to arrays than we've covered so far, and they're really, really useful. And we're also going to talk about how arrays are interpreted on the server, as well as in the language, and how the server interprets arrays. And I want to talk briefly about a class called Server Options, which is your gateway into configuring the server sample rate, number of channels, a few other things like that. And conditional logic. So if then else, and stuff like that. And how if works in the language, and also how if works on the server. Okay. So, but a few things before we get into that. The first thing I want to talk about is you might, in some cases, try to boot the server, and it won't boot. Mine is doing just fine right now, but one strange error you might get will look something like this in the post window. It's something like exception in world open UDP, unable to bind UDP socket, which if you don't know what that means, I mean, you're toast. So how do you deal with that, right? If the server won't boot, I don't know what's happening. So if you see this message in the post window when you try to boot the server, what I recommend you do is type server.kill capital A all. And this is sort of like a hard quit. The reason this happens is I think some of the times, not always, but sometimes if SuperCollider crashes or something, like if the server just quits because you sent it some weird thing that it doesn't know how to deal with, what can happen is the connection between scslang and scsynth, like it was never actually broken, even though the server's down. And so if you try to boot the server, it thinks that there's already a connection there, and it won't let another instance of scslang use the same server. So Server.killAll is kind of like a ace in the hole sort of thing, where if the server just isn't cooperating, you can do Server.killAll, and then you should be able to s.boot again. So that's just something to keep in mind if the server ever gives you trouble if you try to boot it. So we know about help documentation. You can, click on any object, any method, and press Command D, and it brings up any reference files that involve that method or that class. You can also do Shift Command D. And sometimes the documentation is a little bit lacking in some areas, which is unfortunate, but it's sort of the reality sometimes. And one thing you can do in case you might find it helpful, is to type the name of any class and then use the .browse method. And this brings up a this class browser where you can see the name of the unit generator, any class variables and instance variables that it accepts. So you can see syscynth understands AR, KR, and for each of these methods, you can see the arguments that it accepts. So in case anyone finds this useful, that's another thing you can do. It works for any class. So here's the class browser for the window class, etc. Okay. And let's take a look at range methods. And so here is, I want to revisit range a little bit. We've been using range, but let's start with just a simple sine wave. And we're going to plot 1/5 of a second of a 20 hertz sine wave. Lovely. Looks great. Okay, and for a number of reasons, we may want to modify the output range of certain unit generators. No, sc_lang means the language, the interpreter, this stuff here, where we type code and evaluate code. Yeah, sc_lang is the language. scsynth is the audio server. Also, thank you for the host, Kramer Elwell Music. Appreciate it. Okay, so for example, if we use this sine wave and it's going to be controlling the frequency of some other sine wave, the default range is -1 to +1, and that's not good for frequency values. So for example, we might map this, say, range 200 to 1000, and then if we plot this, we can see that we've effectively modified the output range. We've mapped it from its initial -1 to +1 onto 200. A little hard to see, but yeah, here's 200 and here's 1000. Just consider a different example for a second, just so the math is not quite so in high number territory. Let's go from 10 to 20. So this produces a sine wave from 10 to 20, no surprises there. The key point I'm making here is that range is a convenience as an alternative to modifying the output range of a UGen using mul and add. Remember that all UGens have mul and add. So let's get rid of this range method. And syscynth in particular starts with frequency, there's a phase, and then there are mul and add. Mul is a value by which every output value of the syscynth is multiplied by, and add is a value added to each output value of the syscynth. So a question for chat. Everyone watching, let's say we want to produce this same sine wave going from 10 to 20, but we're not going to use the range method. We're going to use mul and add. So what values do we supply for mul and add in order to produce a sine wave ranging from 10 to 20? So chew on that for a second and see if you can come up with appropriate values. Right? By default, syscynth is -1 to +1. We want to scale that by some value. Mul 10 and add 10. Let's give it a try. 10 and that was very close. This goes from 0 to 20 instead of 10 to 20. Let's try mul 5 and add 15. Right. That's good. That's correct. Mul 5, add 15, and we get 10 to 20. So this works because we initially have a sine osc from -1 to 1. Right? There's our initial range. Multiplying by 5 gives us a range of -5 to +5. And then adding 15 simply shifts these values up by 15. So -5 plus 15 is 10, and 5 plus 15 is 20. So yeah, David hit it there. Okay, so what I'm getting at here is that you should do one or the other, but not both, because they effectively do the same thing, right? I usually use one of these range methods like range or exp range because I simply find it more intuitive. I think of my unit generators and signals in terms of how low and high they go. And so I can just specify that directly. And when I do .range, SuperCollider does a little bit of internal math to convert these into suitable mul and add values that do the same thing. So if I was being foolish or careless, and I did something like this, I'm thinking, okay, I just want 10 to 20, so I'll specify mul and add 5 and 15. Oh, and I want the range to be 10 to 20, right? So what we get here is something totally different. This goes from 65 to 115, which is totally not what we wanted. And depending on how you're using these unit generators, it could be kind of explosive, right? So what happens here is mul and add get applied to the sign-osk, and then they get applied again, but using different numbers. So this process repeats itself. 10 to 20 multiplied by 5 gives us 50 to 100, right? And then 50 to 100, add 15 gives us 65 to 115. So bottom line, use a range method if you want to modify the output of a unit generator, or specify mul and add values, whichever you prefer. But if you do both, you're going to get weird stuff. Okay. So that's all I wanted to cover on mul and add. Does that make sense to everybody? Okay. So yeah, add can be seen as a DC offset. That's a perfectly good way to look at it. Yeah, perfectly good way to look at it. I think some of the help files might even compare it to a DC offset or DC bias. Okay. In one of the take-home problems, I think it was number 5, one of the hints is take a look at methods linlin, linexp, explin. There's also lincurve, exp, I think curve lin. DC offset is when you have an AC, an alternating current, or an analog audio signal. It's something which goes above and below 0. And DC offset is simply a vertical shift in one way or the other. Now, in the context of an audio signal that's being sent to your speakers, you generally don't want DC offset because it's a value that offsets the equilibrium point of your speaker, and that's just generally not good for speakers. But for modulating signals, which control frequency or pulse width or whatever, it's perfectly normal to shift those signals up or down. So it's DC, of course, stands for direct current, and it's an electrical term. So if you have some alternating signal and you add some direct current to it, it shifts up or shifts down. So it still alternates, but it's sort of off center. Okay, so these mapping methods are exactly that. They map values from one range to the other. So I want to consider the array 1 through 9, right? Very simply, array 1 through 9. And let's say we want to map these values onto a new range, right? We want to map them so that they're between 100 and 200, right? Well, we can use, well, first of all, let's plot these. We can plot arrays as well. It's just a simple line going from 1 to 9 over the indices 0 through 8. And if we want to map these onto a range of 100 to 200, we can use any of these methods. Linlin, so let's start with linlin, which is a mapping from, we want to start with the input minimum and maximum. Now the minimum number we'll get is 1 and the maximum is 9. So those are the boundaries of our input. So those are the first two arguments to one of these mapping methods. And then we want to map these onto 100 to 200. So we're just going to evaluate this here. And what we get is an array going from 100 to 200, again with 9 items in it, and they are linearly spaced. When plotting an array, does it take the index as the x-axis and the value in the array as the y-axis? Yes, it does. An array indices start at 0. That's correct. So here's one example of using a mapping method. And if we change this, let's also plot this, right? Plot this new result. Again, it's a line. A line mapped linearly onto a new range also produces a line, and it goes from 100 to 200. If we change this to linexp, and we take a look at the result, again, we have numbers going from 100 to 200 in an array of 9 items, but you can see that the spacing of these numbers is exponential, and it's a little bit clearer if we actually plot it. And it's now an exponential curve. So it starts, so its slope is a little bit shallow at first, but then it gets steeper. And if we map these onto some different range, 100 to 1,000, well, there we go. Again, it's exponential, going from 100 to 1,000. If we do exp_lin, this treats this range as if it were on an exponential scale and maps it linearly. So actually, we'll keep this at 1 to 9 to 100 to 1,000. Good question. I'll get to that in 1 second. So this is exp_lin, right? We have some numbers, and we want to turn it into this logarithmic shape. So we map from exponential to linear. Okay, what if the array was from 0 to 8? Yeah, okay, so I think ultimately the question is, what if these numbers are out of bounds, right? So 0 isn't in here, right? So the default behavior of these mapping methods is to first clip incoming values within the expected input minimum and maximum. So it's as if we just send it this, right? So if we do this, and let's take away the plot, notice how the first value produces 100, because that's the minimum. So even if we made this like negative 1,000 or something, right? It still just gets clipped to the minimum of the input range. So it's only going to map values between 1 and 9, and anything above it treats as if it was 9, anything below it treats as if it was 1. Okay, so what if linexp08? Same basic thing. Again, it's expecting a range from 1 to 9, and the default behavior of linexp is to just clip anything coming in that isn't within this range, so that it so this 0, again, linexp applies to every item in this array, and 0, right, is outside of these bounds, so it gets clipped within these bounds. So it gets clipped up to a value of 1, so it's equivalent to just doing this, right? Same result. The reason I'm talking about these mapping methods is because they are really useful with unit generators for taking something and mapping it onto a different range. For example, let's make some sound here. Maybe we'll just plot something. Maybe we'll make some sound. Who knows? I'm unpredictable. Okay. So lftry.ar. Frequency of 8 dot range, or actually, you know what, let's not even do dot range. We're just going to plot this over 0.4 seconds. Okay, so this is 0.4 seconds of a triangle wave running at 8 hertz. And now UGens also understand these mapping methods. So let's say linexp. Now the default range of lftry is -1 to 1. And let's say we want to map this to 200 to 1,000. So same exact behavior. It's as if we just had, we just have values, just numbers coming out of this lftry, and they all get fed into this linexp machine, which takes a number's value along this input range and maps it appropriately to the correct position along the output range based on what kind of mapping we're doing. So if we were to do linlin, question for chat, what would we see on the plot? What would it look like? We know that if we do exp, we go from this linear shape to these exponential shapes. But if we kept it at just linlin, what would happen? Triangle wave. Exactly right. It's got a different range, but the mapping is perfectly linear, so we end up with the same thing, right? And if we were to do explin, then we'd get, okay. So now we're getting into just this one sort of quirk about any range. Yes, it is. It is exactly the same as doing this. The linlin version we just did, identical, indistinguishable. So it is possible to use a range method and then map it if we wanted to, right? So we can string together these ranges and these mappings all day long, right? So yeah, David, it is the same as range. Okay. Okay, so we just got this wacky error, right? I did explin, -1 to 1, 200 to 1,000. And, you know, we don't see anything on the plot. It's a good thing we didn't try to play this. Probably would have sounded horrible. And we get binary operator failed. Float, not a number. Okay, so I think I mentioned this in class and possibly on stream last week. I'm not sure. But we cannot map exponentially when the exponential source range or exponential target range is crosses or involves 0. So as an example, exp range 1 to exp rand. We're going to generate a random number between 1 and 1,000 with an exponential distribution. And this works just fine. We tend to get lower values because it's an exponential distribution. If we make this 1 a 0, not a number, it just stops working completely. And if we say, you know, the array 1, 2, 3, actually, let's do, let's do 1, 2, 3 dot linexp 1, 3 onto -5, 5. So we're mapping onto this exponential range going from -5 to 5. And this is going to fail. Yeah, some weird thing happened here. We get -5, not a number, 5. If this is a 4, you know, okay, something else weird happens here. Yeah, it's basically you just can't do it. And I wanted to have a better explanation in class last Thursday, and I looked into it. And I want to just briefly, very briefly, look at the source code for a class called simple number. And if you type a class and then press Command I, you can see implementations, and the very first one is this class file. And I'm going to do a find for linexp. Okay, so this is how the linexp function is defined. Yeah, that's exactly right. And it has to do with the expression. So here is what linexp returns. It's a power function. So it's this value to the power of this value, then multiplied by this. But I just want to focus on this highlighted section right here. So it's the power of the first argument. Sorry, the first argument raised to the power of the second argument. And so this is the output maximum and the output minimum. And in this case, the output maximum and the output minimum cross 0. Or if they cross 0, that means that this will be a negative number, right? +5 divided by -4. Or as long as they cross 0, one way or the other, this is going to be a negative number. And then the exponent is something divided by something. And so this is very likely to be a non-integer, like 1.5 or 0.2 or something, some decimal value, some floating point number. And it's not meaningful, at least not in the world of real numbers, to talk about a negative number raised to a fractional power. Like, for example, -1 to the power of 1/2. Or, in other words, the square root of -1. There is no value in the real numbers system, which when squared produces -1. So that's the source of these not a numbers, and so it just simply doesn't work. You just don't get a meaningful value. And in the complex number system, okay, but we're not going to get into complex numbers, mostly because I don't know anything about them, and we're going too far down the rabbit hole. And also notice that if outmax is 0, then this value will be 0. And so we're just raising 0 to some power, which always produces 1. And if out min is 0, then we're dividing by 0, and that doesn't work either. So when you use linexp, the target exponential range can't include or cross 0. And likewise, when you use explin, the input range can't include or cross 0. However, there are, we've talked about linlin, linexp. Well, it's been a long time. I did take complex analysis in college, but I know that they are complex. That's about it. So we know linlin, linexp, explin, and expx, right? But there are also these two, lincurve and curvelin, and these can cross 0. So for example, let's go back to our, grab this array here. Let's say dot lincurve 1 and 9 onto -10 to 20. And that works, well, actually, and then with lincurve, there's one more argument that we need to provide, which is a curvature value. We'll start with 0, which makes it linear. And this goes from -10 to 20 with a linear spacing, right? That is the result of our lincurve. Now I'm going to keep that there, and I'm going to change this to a value of 5. This is the curvature value. And positive values cause the curve to curve in one direction. With positive values, the curve changes slowly at first and then quickly. With a value of -5, the opposite happens. The curve changes quickly at first and then slowly. And notice that we are crossing 0, right? So there's no problem here. So, you know, maybe I should just always use lincurve. I've been using linexp and exp this and exp that for so many years, and I've just been avoiding crossing 0 and doing math with these values in order to get what I really want. But this lincurve thing is actually pretty handy. So this is also an option. And the reason I'm talking about lincurve is because I'm basically priming us for our discussion about envelopes, which uses these curve values where 0 is linear and positive values cause the line to bend in one direction. That's a good question. I think, well, when we get to envelopes, instead of numbers for specifying the curves, I think one of the options is the symbol sine, and that creates a sinusoidal S-curve. Or the alternative is to do multiple points on the envelope and curve one way and then curve the next segment the other way. So if you want funky curvatures, probably the right idea on an envelope is to make multiple points, like several points, and then curve however you want. Okay, because somebody remind me at the end of stream, I want to talk about audio rate versus control rate, because there were a lot of questions about that, and I do want to just clarify once and for all what these actually mean and when you use them. So I'm just going to try to remember around 9:30 to get back to that, because I do want to get into some new topics today. And yeah. Okay, so let's clear all this out. I mean, if anybody wants that back, I can undo, but it's going to be recorded, and you can rewatch this to your heart's content. Okay, so let's talk about envelopes and done actions. And we're going to start with, I guess we'll start with a discussion, right? Let's say we've been making all of these unit generator functions, which, you know, produce signal, and they produce signal forever. I can walk away, I can come back 24 hours from now, and unless some disaster has happened, SuperCollider is going to be making this pink noise just, you know, forever. And compositions, pieces of music, don't last forever. They have a finite duration, and all sorts of sounds within a piece of music have a finite duration. So it's just a fundamental thing that we need to do to limit the duration of something. And the way we do that is with envelopes. Primarily, envelopes are used to control the duration of a sound by modulating its envelope. Eric, those are good questions. When we start making envelopes, which is going to be literally in like 5 minutes, you can, we'll make all sorts of wacky shapes. I guarantee it. Yes, that's true. Cage does have an 800-year piece, but that's a very, very special exception to this rule. Most pieces of music don't last that long. Okay. And we've done stuff like, modulate the amplitude of other UGens, right? So now we have this, we basically have these little segments of sound which have a sinusoidal envelope. But what we want to do is make a sound happen once and then done with it, right? And the way we do that is with envelopes. And I'm going to start with a class called env and look up the help file. Env is not a unit generator. It's an entirely language-side object which is meant to represent breakpoint envelopes. It is simply a class, a specification for a segmented envelope. And like most objects, we start by calling the new method on the class, which produces, an env, an instance of env. But, we want to do a lot of stuff to this. We're not just going to take the default here. So we're going to open up these parentheses on env.new. And I'm going to scroll down to the env.new help file. Yeah, here we go. It's class methods.new. Create a new envelope specification. And the first argument to env.new is an array of levels. So imagine we have some breakpoint envelope, right? It's got some starting level. And then, if we're talking about amplitude, it's going to have some level above 0, and then maybe some other levels, and eventually it's going to end down at 0. Yeah, you got to go to the post office then. Okay, so we're going to do the simplest sort of envelope I can possibly think of. Well, maybe not the simplest, but we're going to start at 0, a level of 0. We're going to go to a level of 1, and we're going to go back to a level of 0. Okay, that's the first argument. Those are our levels for this envelope. The next argument is an array of times or durations, however you want to think of it. And the number of items in this array, the number of numbers in this array, is always going to be 1 less than the first array, because if there are 3 points on the envelope, there are 2 segments connecting those points. If there are 10 points, there are 9 segments connecting those 10 points. So this is going to be an array containing 2 numbers, and they're going to be the duration in seconds of the these segments. So let's say 1 second and 2 seconds. Okay. And then curve. And now here's where we just talked about lincurve, and see, I want those pop-ups back. Okay. So basically, this is going to have the same number of items. It can be an array. It can also be a symbol specifying the curvature of all segments. But let's fill it with numbers first. And the first number is going to correspond to the curvature of this segment. And the second number is going to correspond to the curvature of this segment. And I'm just going to specify 0, 0. So this is going to, remember what 0 does in the context of curves? It just makes it linear. So we're going to close this, and guess what's convenient? Env also responds to the plot message. So we're just going to plot this env. And there it is. There's our glorious envelope. It's a specification for a breakpoint envelope. You'll notice we start at a value of 0, we go up to a value of 1, and we go back down to a value of 0. The first duration, lasts 1 second, and the second duration, or the second segment, lasts 2 seconds. And the curvatures are 0. So linear, perfectly straight line, linear, perfectly straight line. Okay? So if you're coding along at home, now is probably the time that I imagine people would just start tinkering with these numbers. And that's perfectly, there's a lot of windows here. Let's do window.closeAll. Okay, they're gone. So first of all, let's make this duration 10 seconds. And there it is, right? It's always scaled to fit within this window, and you can resize it however you want. But now we have a 10-second linear release instead of a 2-second linear release. And let's make this -4. So this changes the curvature of this 10-second release, this 10-second segment number 2. And negative numbers, remember, cause curves to change quickly at first and then level out. So now we have this sort of shape. Yeah. And if we, let's see, let's shorten this duration a little bit. All right, still got the same -4 curvature. And let's change this to a +4. And this is going to curve the envelope in the following way. Again, positive numbers cause the curve to change slowly and then quickly. Negative numbers cause the curve to change quickly at first, then slowly. So if we reverse these, we've just sort of inverted both of those curvatures. So let's see. We can add some more segments, maybe. Let's have it go down to 0.5. We'll have it go down to 0.5 over 2 seconds. And that will be linear. And we'll maybe return these to their original positive-negative orientation. Okay, so before I run this, just think about it in your head and try to imagine what it's going to look like. So we go from 0 to 1 over 1 second with this curvature. So it's going to change slowly, then quickly. And what happens if you don't send a time for the new point, like this or something? You know, then I think we. Good question. It just fills it in. That's weird. Yeah, it's 1 second, and then this is 5 seconds. I think it must default to a value of 1. We did this. Yeah, fills it in with stuff. I don't know. So I guess it doesn't give you an error message, which, quite frankly, I think is kind of annoying. It should let you know that you don't have the right number of things in your array. But yeah, so code responsibly, everyone. So okay, so we go 0 to 1, down to 0.5, and then down to 0. So 1 second attack, 2 second middle segment, 5 second release, curve, linear, other kind of curve. So it looks like this. Here's our curve 4 segment up to value of 1. Linearly, we drop down to 0.5 over the course of 2 seconds, and then a 5 second release. Okay, so I think we all get the idea. These are envelopes. This is how you make them. There are a few other methods you can use for env other than new. It's actually quite a few of them. For example, there's, what are some interesting ones? Triangle, env.triangle, env.sign, env.perc for percussive. Okay, but we can tinker around with these all day. I sort of think of new as the most flexible method for envelopes, because you get to specify exactly what you want, and you're not limited by some. I mean, these are also convenient. If you just want like just a simple percussive envelope, you can just say, you know, env.perc.plot. Boom. Very, very short attack, long release. Right? Total duration of 1 second. So env.triangle. Surprise, surprise, it's a triangle. Okay, so let's use this in a unit generator. Now we can't use env as is in a sound function, something, you know, function.play, because it's not a unit generator and it has a static quantity that only really makes sense on the language. So what we do is we use or declare an envelope variable. So we have sig and env. And we can't say env equals env.new. We have to wrap our variable in the unit generator envgen. And we'll go with kr. This is short for envelope generator. Now this is a unit generator. It outputs a signal based on the envelope provided for its first argument. I know it seems a little confusing. We're putting an env inside of an envgen, and, you know, can't we just keep it simple? Well, you know, that's just the way it is, and it's something you'll get used to. So the arguments for envgen first are, the first argument is envelope. It's an env instance, and we already know how to do that. So I might as well put this on a new line just for a little bit of clarity. So env.new, we'll go 0, 1, 0. And let's have a short attack time, maybe 0.02. And the seconds again. And we'll do a 1.5 second release. And our curve, well, this first segment is just so short. The difference is going to be very, very subtle here. All the same, we'll just keep it linear. And then we're going to, we'll keep this, maybe make this curve sort of quickly down and then level off a little bit. We can actually even plot this. So that's what it looks like. It kind of looks exactly like that percussive envelope we just made. If we call the variable other than env can be, oh, sure. I mean, well, you can call this whatever you want. You can call this like blah. I mean, variable names are just whatever you want to make them. It's just, it's sort of good practice to make them mean something. And, you know, maybe it's a little confusing that I'm using env here and env here, but this is just a habit I've gotten into. I just love these little three-letter variable names. But this could be whatever you want, the name of the variable. Okay, so let's get rid of that plot. And we could stop here, actually. We can just close out the envgen. Really, all we ultimately need for an envelope is just an env specification inside of a unit generator, specifically envgen. Okay, so now let's make our signal. Sig does not equal sig, not yet. Okay, first it's got to equal something. So let's just do a sine osc at 500 hertz. Okay, and then all we need to do is sig equals sig times env. We might as well, you know, make this stereo somewhere along the line. And I'm also going to multiply this by 0.2, just so it's not super loud. Because remember, this envelope goes all the way up to 1. And without any sort of additional scaling, it's going to be maximally loud. And, you know, I just generally try to avoid that. I just think there's no reason to have something just at the ceiling. Okay, so I'm trying to keep this fairly simple. That works. That's really all there is to envelopes. That's the gist of envelopes. So yeah, we can just run it as often as we want, and the sine wave just sort of finishes. Okay. So we might think we're done. We figured it out. We figured out envelopes, right? Wonderful. I can do this all day. It's like someone's ringing the doorbell trying to get in. Okay, now what I want to do is bring up the node tree, which is that little window with the gray and white rectangles that shows what's living on the server. Now we don't hear anything. We don't hear anything whatsoever, but let's do s.plot tree. This is one of those tools, and whoa, we've got company, right? So we actually, I ran this code 7 times, and sure enough, we have 7 synths running on the server, right? Let's tuck this over here. Maybe make it a little smaller. I know it's kind of hard to see. I'll just shrink this a little bit. Let's run it again. And you'll notice that we just keep adding to the party. More guests are arriving. Here they come. I hope we brought enough food. So what's going on here? You know, if we kept doing this, actually take a look at the CPU meter down here. This second number here, which is like hovering around 1%. If we keep doing this, you know, okay, I'm not going to sit here all day and do this, but take my word for it that eventually this CPU percentage thing will get higher and higher. And once it gets close to 100, you're going to start hearing sample dropouts and the audio is going to start getting crappy. And so that's no good. So let me explain what is going on here. We create a sound function. which produces a sine wave multiplied by this envelope. And this envelope signal goes from 0 to 1 to 0 over the course of 1.52 seconds. And then it arrives at its final destination, 0, and it just sits there. And there's nothing telling this sound process to free itself, right? And, earlier in the week and last week, we'd call this, x, and then we'd say x.free, but we haven't freed anything here. And, we just, if we're being sort of careless, we're like, oh, we don't need to free anything. There's no sound happening. But there sure is. It just happens to be all 0. So let's do s.freeAll first of all, to just wipe everything off the server. Right? It's gone, and now we get to start fresh. Okay, so that's just a clean way to destroy everything. Okay, so this brings me to the sort of other half of the world of envelopes, right? And other UGens. These are called doneActions, and I think there's a help file called UGen done-actions somewhere. Yeah, okay. UGen doneActions. Doneactions are, well, the UGens that are inherently finite. Example, envgen, and some other things, line, xline. These are just simple generators that make a segment of a line from point A to point B over a certain number of seconds. And other stuff that in its design is inherently finite, has an argument called doneAction, usually at the very end. And a doneAction is an integer which tells the synth that is enclosing that unit generator what to do when that finite UGen has reached its end. So the default doneAction for envgen, where am I going here? Yeah, is 0. Okay, so all I've done is specify this env. I haven't specified gate, level scale, level bias, time scale, or doneAction. So it's using the defaults for all of these values. And the default doneAction is 0. So let's go back to this UGen doneActions file and take a look at the action. So 0, a value of 0 for a doneAction means do nothing when the UGen is finished. And that's exactly what the server is doing. The envelope finishes. The envelope checks its doneAction, or maybe the server checks the doneAction and says, oh, 0, do nothing. So it just leaves it there. It leaves this silent synth, this silent sound function just on the server, spitting out zeros at the audio rate, just not going to touch it. And that's not really what we want to do. If we're using an envelope to modulate the amplitude of a sound so that it has an attack and a release and then it's done, what we want to do is free the synth. And we want to take this function.play and we want to say, oh, your envelope is done? Go away. Go off the server. Get out of here. And so that's what we do. There are a whole bunch of other numbers for doneActions. And I'm going to be perfectly honest with everybody right now. I have only ever used 0 or 2. That's it. Other numbers do different things. They tell the synth, okay, do this wacky thing when the envelope is finished. But all you really need to know is that 0 means do nothing, and 2 means free the synth. So let's go ahead and specify that. Now, the first argument here is envelope. Sorry, right? Oh, geez. Okay, envelope. Then we have gate, level scale, level bias, and I don't want to really talk about these just yet. So I'm going to skip over these, and I want to just specify the doneAction, and I can do that. What are the nodes? Oh, you mean like do you see node on screen somewhere? Because node actually means two things. There's nodes inside the env class, and then there are nodes on the server. When we play the sound function and we look at the node tree, yeah, I'm guessing that's what you're, yeah, s.plot tree. Nodes are, for lack of a better way to explain it at the moment, the rectangles, right? So the server, the audio server, is this invisible process which handles all the audio signals, all the control signals, makes all the sound, and it just runs invisibly. We can tell with these green numbers that it's awake, that it's active, that it's doing stuff. And we can sort of visualize the processes that are currently alive on the server. We have this group, that's a node, and we have this single synth, which is currently producing zeros, that's a node. And when we get to server architecture, trust me, you're going to be so sick of nodes. But for now, just they are individual entities that or processes that are living on the server. Okay. So as I was saying, I want to we provided the envelope for envgen, and I also want to provide doneAction too. And to skip over all of these intermediary arguments, I just do a comma, and then if I just provide 2, it thinks I'm providing that for gate. So instead, I'm going to say done capital A action : and as you can see, it actually switches over to doneAction here. So now it knows I'm telling what the doneAction should be. Okay, so we have our env, and then we have doneAction too, and that is sufficient. So let's plot the tree one more time. Let's do s.freeAll. Okay, so now we have our node tree. And now, watch this. I'm going to play this sound function. I want you to keep an eye on this window here. Ah. And now we can, play our little fasten seatbelts. Doors are closing. Please step back. And we don't even have to give this function a name anymore, because we're not going to be freeing it because it frees itself automatically when the envelope is done. So this is crazy convenient. I mean, it's all of a sudden we can just put all sorts of arguments in here and do all sorts of modulation. And then we can, maybe we'll save this function as f equals, this function. Boom, there it is. And then we can just say f.play whenever we feel like it. Right, there we go. Maybe we go down here and we code some other stuff. Come back, we want another sine wave. So, and we never ever have to worry about synths piling up on the server and hogging CPU, because whenever they're done, they're done. Okay. All right. So let's see what is next. Oh, okay. There's so many things to talk about here. Let's make an argument here. Remember we made an argument called freak. Right, and so then if we say f.play, it's 500, but we can also do args : freak 600. Right. Right. So now we can specify the frequency when we play the function, and we can also specify, for example, maximum amplitude, attack time. Let's actually do that. Attack and release. And we have to declare these as well. Attack by default 0.02. Release is 1.5. Right? So I've preserved the values that were hard-coded into the envelope, and now I've declared them as arguments. So now, let's go back to 500. Let's do 350. 350. Why not? And when we play a function that we've already defined and call its arguments, we can just continue specifying. Let's do 0.5. Right, so now it's going to have a frequency of 350, and the attack time, we're going to override that default value and instead have the attack time be 0.5. Maybe 1. And maybe we'll have the release time be a whopping 6 seconds. And we'll make this even shorter. We can also specify something like release curve. So I'm adding a release curve argument, which is -2. Okay, side note here, watch this. Oh, error message. What did I do? What did I do wrong? Let me clear this post window and do it again. Okay, error, syntax error, unexpected, binary operator, expecting ellipsis. Rah, rah, rah. Okay, the problem is this. It's this equal sign immediately followed by a minus sign. And it's like trying to interpret this as some sort of, operator. there's a couple solutions here. When your default value for an argument is a negative value, you can just enclose it in parentheses, and that fixes the problem. This is really, it's really strange. I think some of my students also found out that you can do this. You don't even need the equal sign. You can just put everything in parentheses, which I did not know. I had no idea. Apparently this is valid. So, but what I've gotten in the habit of doing is just a negative default values go in parentheses. I think you can also put a space. This is one of those rare cases where SuperCollider actually does look at white space. Normally, it completely ignores it, and it doesn't get mad if you put spaces in all sorts of weird places. But yeah, space also works. But this is not allowed. This argument name equals minus. Yeah. So that's one of those things where if you don't know what's going on, you're going to tear your hair out looking for the problem. Okay. So now I can set the, let's see, make the release time 3. And it's got a 3-second release, and we'll also say rel curve minus 10. And you can see the amplitude drops down very quickly and then levels off. So 20, 30, 40, So if we were to plot this, we'd see the release. Even though it's 3 seconds long, it sort of shoots down real fast and then levels off. And if we do positive values, it basically stays level for a while and then drops off right at the end. And, probably one of the most fun things you can do is instead of specifying a value, a hard-coded integer here, you can do exbrand, whatever. And you can put random values here so that maybe they are very short and maybe they are very long. Oh, not exp. Jeez. Wow, that could have been bad. Exbrand. Oh, see, that was a short attack time. You get the idea. All right, so this is creating a sound function. We've got an envelope in here. And just 2 more quick envelopes. Instead of envgen, you can also do line. Line.kr. Let's go from 1 to 0 over 3 seconds. And notice that line has a doneAction as well, right? DoneAction equals 0. So we're just going to say doneAction : 2, right? And we've just swapped out envgen for a line. So this is, we'll actually play this. Right? So 3-second linear decay. We can do X line, but remember we have a 0 here. So this is going to fail. In fact, I think if you play it, it's just silent. There's like some safety thing here instead of like negative infinity amplitude or God knows what. But this will fail. Like for example, if we try to plot this, yeah, we just get like 0, or it's just flat, or it doesn't look correct. If we change this back to line, then yeah, this is fine. It's a line. So just with X line, we can't include or cross 0. So we'll just set this to 0.001. Right. Okay. That's envelopes. Let's do one more thing with envelopes before we move on. Just want to show you we don't always have to do env.new. Like we can do one of these sort of make room for ourselves here. Here we go. Let's go back to the env help file, and let's take a look at the method there are several sustained envelope creation methods. Now, env.new is finite. It can't sustain. You can't say, oh, by the way, and also hold at 1 until I tell you to stop. It's not gonna. It's just gonna go attack up to 1, release down to 0, and then it's gonna check its done action. But there are some env methods. Probably this one should be familiar to most of you, ADSR. Good old friendly ADSR envelope. So we provide, it's totally different, right? There's no arrays or anything like that. So let's just start fresh here. env.adsr. So we have an attack time. We already have attack declared as an argument here. I'm just going to put it right in. Then we need a decay time. Right? So we ramp up to an initial level, and then we decay down to a sustain level. So let's just go with this 0.3, and it's going to sustain. Let's have it sustain at 0.2, so kind of low. So this is, so we're going to hear this quick boo. It's going to pop up, be kind of loud for just a fraction of a second, and then it's going to sustain down at a level 0.2, and then we'll keep our release time. And so attack time, decay time, sustain level, and release time. And that's usually all I provide. Okay, and then because this is a sustaining envelope method, we need to provide a gate. A gate is basically it's going to be an argument. You might as well declare it right now. Gate equals, we'll set it equal to, no, we'll set it equal to 1. Initially, gate is going to be 1. So gate is a value. Let's see how it describes. Oh, that's an envgen argument, right? So the first argument of envgen is this actual env. Then next we have a gate. So gate, this triggers the envelope and holds it open while greater than 0. So it's going to start at a value of 1, which means it's going to go up, and we're going to do our attack, our decay, and sustain at a level of 0.2 as long as the gate is greater than 0. If the env is fixed length, then it just serves as a trigger to start the envelope, and then it's on its own. And if it's a sustaining envelope, for example, env.adsr, then the envelope is held open until the gate becomes 0, at which point is released. So we stay here at a level of 0.2 until gate becomes 0. Okay, and then of course, once we do set the gate back to 0, we're going to do this release phase, and it's going to get to the end of the envelope. And so then we need to say doneAction 2. Right. Okay, so I'm just going to run this, and then we'll say sound equals f.play. So we are live. We've got a sine wave, and its amplitude is controlled by this envelope, and gate was 1 initially, and so the envelope started and is now at its sustain portion. And we fortunately decided to give this f.play call a name. So this synth we've created is tilde sound. So we can say tilde sound dot set. Remember the set command? Gate 0. So we are updating the, sorry, not that one, this one, the argument of our sound function, which is initially 1, and now we're going to make it 0. And this triggers the release phase, which is going to be 1.5 seconds long, and then we're going to free the synth. There it goes. Right. So this comes in handy if you're ever using, for example, my MIDI controller is no longer here. I moved it to a different room. But if you're using a MIDI controller to to generate sound on the server, you probably want to use this ADSR envelope because you press a key down and you want that sound to sustain indefinitely until you release the key. And then that causes the release to decay. So that's it's useful here. But if you just want to generate a bunch of autonomous sort of finite duration sounds, then you just use env.new and doneAction2, and they have a finite duration, and as soon as you start them, they're on their own, they go off, they do their own thing, they end after a finite duration, and then they free themselves. And okay, I promise this is the last thing I'm going to do with envelopes. You do not always have to control amplitude with envelopes. Let's go back actually to our env.new. I'm going to copy this guy here and put that in there. So now we have. All right, so let's make this. No, let's keep that where it is. We'll make this a really, really quick attack. Now, yeah. Whenever you do function.play, it automatically adds a short, what is it, like a 0.02 second fade in. So I'm just gonna fade time : 0. And now you can really hear that 1 millisecond attack time. Yeah, function.play is a convenience instead of actually creating a synth def and a synth. I think we'll probably get to that next week, but I just want to show you this actual attack time here. All right, so let's make this release 5 seconds. And we'll make the curve like -5 or something. Okay, and let's make a variable called freak. Oh, we can't actually do that because we actually have this thing here. So I'm going to delete this. Freak is no longer an argument. We can't specify it as we were doing up here. Instead, it's going to be a variable. And it's going to be envgen.kr env.new. And this envgen is going to control the frequency of the sine wave. Now, normally we put things like other sine waves in here, maybe LF pulse or LF noise 0, LF noise 1, just to sort of bloopy bloopy bloop, you know, make the sine wave do funny things. But here we're just going to do like a strict glissando. So maybe we'll go from 200 to 800 down to 400. And we'll take 1 second to get there, and then 3 seconds to get down from 800 to 400. And I think here we can just specify, well, let's just keep the, let's do 3 and -3. And we can plot this. Yeah, so here's our frequency envelope. It starts at 200, it goes boop, it just goes up and halfway down. Well, maybe not halfway down, exponentially halfway down. So, okay, let's get rid of that plot. And we can close this out. Now, we don't really want a done action here. We can just leave that at 0. So this should be sufficient. Yeah. Now let's make this go down to 400 faster. Maybe even faster. Yeah, okay. And if we now, okay, so here's yet another question for chat here. What if I do this? What if I say, by the way, freak envgen, your done action is not 0, it is 2. Okay? So what is going to happen here? Before I play this function, I want you to think about it. We've got a done action here, which is, you know, so the synth gets freed. That's what done action 2 does after 5.001 seconds. But this also has a done action 2, and it's got a shorter duration. So what is going to happen? Anyone? It's going to explode. Going to kill the server. Going to crash my computer. It'll free the synth on the shorter duration. Correct. Whoa, where'd my sound go? Right? So this envelope wasn't finished. Right? It was still in the middle of its, yeah, Logan Smith. Nice. Yeah, we ended early. It's exactly what's happening. This envelope is longer. It's got a total duration of 5.001 seconds. Now, when it's done, it frees the synth. But this one beat it to the punch. It's only 0.4 seconds long. And when it finishes, it checks its doneAction, and it says, guess what? We're out of here. We're done. And this whole sound function, everything that is enclosed in these curly braces, that entire process just vanishes. Right? So this envelope didn't even get a chance to finish. So there it goes. You know, so we get this click at the end. Now, if we remove this, or maybe comment it out, then when this envelope gets to the end, its doneAction is now the default value of 0, so it does nothing. It just continues, right? Whatever, it doesn't even know what else it happens to be doing, but it just knows not to do anything. And then this one is sort of the longest envelope, and it's sort of the governing process. It's the one that controls the amplitude, so when it is finished, it goes all the way down to 0, and then we hear no more sound. So that's the right moment to do doneAction 2. And this is just to reinforce here. UGen is just an envelope generator. It just generates a signal, you know, from any sort of values in any sort of curves you want, and it can be used for anything. It can be used for frequency, amplitude, width of a pulse wave, or you know, the phase of a sine osc or something. So all sorts of interesting stuff. And I think Eric had a question about, let's do end.new. So if we want to go from 0 to 1 to 0, 1 second, 1 second, instead of an array of curves here, we can specify a certain symbol. And in the env help file, where is it? Yeah, so for curve, a symbol, a float, or an array of those determines the shape of the envelope segment. So you can do step, which is going to be non-interpolation. It's just going to jump immediately to the value. Hold, linear, exponential. There's sine. So let's see what sine looks like. Dot plot. Yeah. So it's, I don't know if this is what you're talking about with an S-curve, but it goes from 0 sinusoidally up to 1, and then sinusoidally down to 0. This sine option applies to all segments. So if we just have 0 to 1 over 1 second and do sine, then you know we get this S-curve, sinusoidal curve. So there you go. And there's some others. There's Welch window, squared, cubed. Yeah, so you have a lot of options. Okay. All right. New topic. And this is a short one. I think I can get through this and then talk about arrays a little bit. So randomness. We know that we can make random numbers like this. Right? So rrand is a linear distribution, which means we're fine including 0. We can even include negative numbers. And this just picks random numbers between these values inclusive. Exprand chooses random numbers with an exponential distribution, so tending towards lower values. And if we cross or include 0, it fails. So we have to stay in the positive range here. Okay, here's an interesting quirk about rrand. If the minimum and maximum are integers, the result is always an integer. No, I guess there's no handing window. I know, that is a little strange. Usually SuperCollider is pretty comprehensive. But, I mean, it's a subtle difference. So, but yeah. I guess you can always make your own. It's open source. Okay, so when rrand, when you provide integer values for minimum and maximum, we get ints. If we provide floats, even if, you know, technically it's the same, equal to an integer value, we get floats. And if only one of these values is a float and the other one is an integer, we still get floats. Okay? So if you want integers from rrand, you specify integer minimum, integer maximum, and you get integers. If one or both of these numbers has a decimal point, you get floats. Okay? Xbrand, you probably already noticed, always produces floats. But you can always use the round method to turn them into integers. Right? And you could also, so the default here is a value of 1, which rounds it to the nearest integer. But you can also round to the nearest tenths place or hundredths place. So that's how round works. So you can get integers or floats out of either of these. You can even round to the nearest, it's basically rounding to the nearest multiple of the argument here. So it's going to round to the nearest even number here. Okay. Now, now we know, we're going to get into arrays a little bit here. We know about the exclamation point, which is a shortcut for the .dup method, right? So for .dup2, not 21, 4.dup2 gives us the array 4, 4. 10.dup5 gives us the array 10, 10, 10, 10, 10. And the exclamation point shortcut is exactly that. It is a shortcut receiver duplicated that many times, right? Okay. So that's duplication. It's a quick way to create an array by copying a thing. Now, okay, this is a very interesting quirk here. 1, 100. What happens if we do this? You can evaluate it if you want, if you got SuperCollider open at the same time. What happens here? rand 1, 100 exclam 5. Now, one of two things. I don't know. It's just not sure what everyone thinks is going to happen, but here's what happens. You ready? Get the same number in each duplication. 5 of the same random number. Right, because of this left to right thing. So the first thing that the interpreter sees is rand 1, 100. Bam, it does that, and then it duplicates that random number 5 times. Right? But what if we want this? How do we get this in a non-stupid way? So I've just, manually made the array containing all these things, these identical. This is not how you program efficiently. But how do we do this? Right, essentially make a loop. We want to get SuperCollider to actually evaluate this code, this rand command, 5 unique times. Because if we do it ourselves, 1, 2, 3, 4, 5, well, there we go. But unfortunately, we can't just exclam 5 it and get random numbers. Okay, so I'm going to explain the solution here. I'm going to show the solution, and then I'll explain what's going on here. What we do here is, does the exclam 5 thing show expansion last week? Like, does it work on unit generators and signals? And 5. Yes, it does. If that's your question, like if you do, a function signask.ar exclam 5, yes, it will create an array of 5 sign oscillators. This is multi-channel expansion, and I'm going to try to get into this. All right, here's the fastest way to fill an array with 5 unique random numbers, or uniquely generated random numbers. You put the random call in a function. Look at that. Okay, so why does this work? Now, if we look up the help documentation for DUP, we can see that it's actually defined for 2 classes, object and function. And for object, duplicates the receiver n times, returning an array of n copies. Hint, hint, different classes interpret this message differently. The shortcut exclamation point can be used in place. Okay, so object is the abstract superclass of all objects. And in object-oriented programming languages, there's this idea of inheritance, where objects which are subclasses of other classes inherit the superclass's methods. So if something is defined for object, for example, the DUP method, it's defined for all of object's subclasses. That's why dup works with everything. You know, it works for floats. It works for strings. Exclam5. It works for everything. Everything knows how to duplicate itself, right? But for the function class, so here's the function help file, and we go down to dup. So function behaves a little bit differently when it receives the dup method. Not only does it duplicate itself, but it also evaluates itself for each duplication. Oh, David's going crazy over there. Okay. So this means, like, you know, if we do this, you know, when we evaluate just this function without the exclam5, what we get in the post window is a function. So, you know, intuitively, it seems like if we evaluate this whole line, function exclam5, that we would get something like this in the post window, right? We would just duplicate our function because that's what it is. It's a function. We're not calling value on it. But the key here is that functions respond to duplication by not just duplicating themselves, but also evaluating themselves. So that's why we don't just get 5 functions, we get 5 evaluations of a function. And those evaluations happen for each duplication. Okay. Yeah. Well, I can't help myself. Let's see what David has come up with. Oh yeah. Okay. Yeah. Interesting. So first, what happens is we have this random value between 1 and 100, and we create 5 unique copies, right? Then we put that in a function and duplicate that 4 times. So we get an array containing 4 arrays, and each one of those internal arrays contains 5 random numbers. So yeah, nested function duplication. Very nice. All right. So let's talk about arrays. We're talking about randomness, but we've sort of transitioned into the dup method, and we should really talk about arrays. Array is, you know, easily one of the top 5 most useful classes in SuperCollider, and really in any programming language, because array is an ordered collection of things. So if you have a lot of things that you're working with, and you want to be able to manage them in a nice organized way, you should probably think about putting them in an array, because then they become one unit, one unified thing, you know, which has an order, and you can address and change and modify and add and remove items from the collection however you want, right? So array actually has a long inheritance list. It starts with object, goes to the subclass collection, then sequenceable collection, arrayed collection, and finally array. So every method which is defined for all these superclasses is also defined for array. So it's just something to keep in mind. First of all, let's talk about creating arrays. One thing you've seen me do already is just make it yourself. Square brackets. That's how we delineate an array, and we can say 1, 6, 9.3, 100, 0.001. Right? And there we go. We've got an array called X. It's globally accessible, and you know, we can you know, reverse it. Now it's backwards. We can double reverse it, and now it's forwards again. It's a pretty silly thing to do. So that's one way you can make arrays. The other methods, you know, you remember that, you know, for example, env, if we say env.new and window.new, okay, we can also do array.new, sort of. New clear is something that I've used from time to time, and we provide a size. Let's say we want it to be 4 items long, and this gives us an array of nils. Probably we should store this. So now X is equal to this array containing 4 nils. And then maybe we can change these values if we want. So if you want to start with an empty array, that's a pretty okay way to do it. You can also do X equals array.fill. So this is a method which fills an array according to a function. So we tell it how big do we want it to be. Let's say 6. and we provide a function. And so here we could, go back to our random tools. So we are going to fill a function. It's going to contain 6 things, and each thing is going to be a result of the evaluation of this function. So we will get 6 unique random numbers. There we go. Maybe I'll round these. Right? So we're going to tend to get sort of low numbers because it's exparand, but every now and then we'll get some high number close to 100. Now, what if we take these curly braces away? Right? Question for everybody out there. I've removed the curly braces. So what is this line going to return? What are we going to see in the post window? Array.fill, 6 items. Here is how we fill it. What's it going to be? Same numbers. Exactly. What happens here is that it knows it needs to fill an array, and so it evaluates this thing. And it says, oh, it's 43, an array of 6 43s. But if we put it in functions, then that function is evaluated for each slot that needs to get filled. So we get random numbers. Okay, so that's array.fill. A few other fun array creation methods. Array.series. So again, we start with a size. Let's say 10. We will start at a value of 1, and the step size will be 2. So this creates an array of 10 numbers starting at 1, increasing by an arithmetic series with a step value of 2. So we get 1, 3, 5, 7, 9, etc. And if we step by 8, then we get 1, 9, 17, 25. And we can also start at, say, 100 and step by 250. So this is a quick way to algorithmically generate an arithmetic series. And the related method here is array.geom, for a geometric series. So let's say 10, start at a value of 2, and instead of adding to each successive item, we're going to multiply. So we'll do 3. This might be kind of large. Yeah. So we multiply each item by 3, starting with 2. So 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54. So we create a geometric series in this way. And the last neat little shortcut for creating arrays is parentheses, interestingly. And we do the start value, and we do period, period, end value. Let's say 13. And then we close the parentheses. And, it looks like this is going to give us some syntax error, because it's like, what do you mean double period? What's that all about? But if we evaluate this, we get the array 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this is just simply a start to end. We can even go into negative numbers here. So we get -5 to 13. And if we don't want integers, we can specify the, let's say, let's go 1, comma, 1.1, comma, 10. Oh, sorry, not comma. 1, comma, 1.1, dot, dot, 10, close parentheses. Oh, yeah. That's an unfortunate unfearing. Thanks for pointing that out. Yeah, the help file does have a dot, dot here, and that is just a coincidence. I wish it said something like initial phase offset in cycles, period, expects a value between 0 and 1. This dot, dot is a little bit confusing. It's not related to the syntax shortcut like this. Okay, so here what we're doing is we say 1, comma, and then the next value, then our dot, dot, and then the ending value. And this gives us 1, 1.1, 1.2. So this provides the interval. It's a little bit like array.series. Yeah, maybe they did mean to do three periods, a true sort of ellipsis. There's some more questions in chat. So curly braces only defines functions. Yes, that's exactly how we define functions. If something is within curly braces, then we have a function, and the code inside is what gets evaluated if we call dot value. Can you use the dot, dot with brackets or just parentheses? You cannot do it with brackets. That's a syntax error. 1 comma 10 is fine. It's the array 1 comma 10, and the array 1.10 is the number 1.1, but dot dot doesn't make sense. It's a little bit counterintuitive that we're using regular parentheses to make an array, which is in square brackets, but that is how it works. Yeah, so just parentheses. Right. This is the shortcut to create the array 1, 2, 3, 4, 9, 10. Right. Okay. Okay, so that's how we create arrays. Let's take a look at this one here. So we now have our, let's do it again. I don't want any duplicates. Ugh, just give me these duplicates. Okay, there we go. All right, so let's just clear all this stuff for a second. So we've just made an array called x, and it is the numbers 40, 1, 12, 4, 53, 35. And let's say we want to access one of these items. Well, we do x dot at, and then the index. So this item here has index 0, index 1, index 2, index 3. So if we say x at 0, this returns 40. If we say x at 3, this returns 4. So this is accessing items in the array. And as a shortcut, you can do x, and then immediately after it, square brackets, and the item in the array. So x at 0, x at 1, x at 2. So we're simply indexing into the array and say, hey, array, what do you have at index 5? And it says, oh, at index 5, I have the number 35. All right, and then modifying arrays. Right? There's all sorts of things we can do with arrays. We can, I think we've seen this before, x dot squared simply squares each item in the array. But there's some non-mathematical things we can do. For example, x dot size. It's always a pretty useful thing to know how big an array is. So this returns 6 because there are 6 items in the array. So that's size. Maybe I'll keep x dot squared for a second. Right? And let's see what else. Oh, okay. X dot sum. What this does, right, here's x. X dot sum returns the sum of the items inside of it. So all these numbers added together, 145. We can also do an average or a mean of these values with x dot mean. So the average of these 6 numbers is 24.16 repeating. And okay, probably one of the more common ones is x dot add. X dot add. This is how we change the size of the array. And I'm gonna start over with a new array here. X equals 1, 2, 3. The array 1, 2, 3. Okay, so we're gonna say x dot add a random number between 1 and 100. So here we go. Here we go, and we can verify that x has actually been modified. Now x is the array 1, 2, 3, 23. Let's do it again. Okay, there we go. Oh, wait a minute. Okay, so here's a very subtle thing about add, which kind of gets at the some sort of underpinnings of how programming languages allocate memory space. So when we make an array, what happens behind the scenes is the computer says, okay, I'm allocating the following space, which is suitable for 3 items, three integers, right? And in a lot of programming languages, you've got to say, okay, this array contains floats, or this array contains integers, or this or that, and different items have different sizes and things like that. But SuperCollider takes care of a lot of this for you in the background. So now we can see, x dot size, it's 3, and we'll add a random value. Right? And oh, it actually happened to add the number 1. How interesting. And so now the array is size 4. If we do this again, we return the expected result, but it doesn't actually modify the receiver. The size is still 4, and it still only contains 1, 2, 3, and 1. So how do we actually make sure that when we add a number, it actually gets added and increases the size by 1? Well, the secret here is to actually overwrite that global variable. And so if we don't do that, it's using the same memory allocation, which it's only allowed to use a finite size, and it can only expand so much. But if we say x equals x.add, then this is SuperCollider's cue to say, okay, reallocating memory space for that is enough space for this new array, which has a new thing. So let's just watch this again. Here we go. And now we'll say x equals x.add. We get a 79. And can verify, sure enough, it's there. Add another thing. Here we go. Keep adding, and we can just add all day long. And as long as we make sure to overwrite the container holding that array as we add, then we will always remain positive that the array is in fact being increased. So that's array.add. Okay, I realize it's we've gone at least an hour and a half now, and the last thing I want to do, and I'll stop at 9:45. Let's get into arrays on the server and how the server interprets arrays. The server interprets arrays as multi-channel signals. So, for example, you know what we've said sig equals sinosk.ar 500 0.2, and we play this. If we don't do any exclamation point 2 or any arrays, everything is just completely monophonic, as you can see. And probably here, if you're on headphones, we just have a single channel. If we do exclamation point 2, we get both channels. And if we just run this, we can see, sure enough, we have an array. Okay, it doesn't technically say sinosk, but don't worry about that. This is just some server behind-the-scenes stuff. You can see that it is, in fact, an array of 2 UGens. So the server, when it tries to play a function that returns an array of unit generators, it says, okay, this must be a multi-channel signal. Like when it's an array of 2 things, it says it's stereo. Okay, so the thing at index 0 gets assigned to output bus 0, and the thing at index 1 gets assigned to output index 1. And if you had an array of 8 unit generators and 8 speakers and an audio interface with 8 outputs, then it would just assign those signals down the line. And this is not a very interesting case because we're just duplicating a sine wave, which is completely deterministic, and it's always going to be a sine wave. It's always going to have the frequency we provide for it. But you know, let's do something a little different. Let's say sig equals the array. We're going to manually make an array ourselves, and we're going to fill it with a sinosk and pink noise.ar with an amplitude of 0.2. Okay. And now we don't need to do any exclamation point 2 because we've sort of created an array ourselves. And index 0 is a sinosk at 500 hertz, and index 1 is pink noise. So this is sort of very, I don't really like listening to that. My ears are getting 2 completely different things, which is a very unusual thing. But yeah, you should be able to also see in the level meters that the levels are in fact totally different. Sorry. Here's our sine wave. Here's our pink noise. Okay. And so here's something really interesting. The way there is a help document called multi-channel expansion, which sort of explains this. So I would recommend you read this. And it sort of goes through, and well, I think one thing it says is that multi-channel expansion will propagate through the expansion graph, or in other words, through the unit generator function. So basically, if we now say sig equals sig times, let's say lfpulse.kr 5. maybe we'll slow it down a little bit. Meters. So what's happening here is that we have an array containing 2 unit generators. And then step number 2, it says multiply this array, sig is an array, by the single unit generator, LF pulse 1. And so now it's trying to multiply an array with 2 things by an array with 1 thing. Or, well, not even an array of 2 things with 1 thing. And the way it handles that is it multiplies the single thing by both items in the array. And so both of these get modulated by the LF pulse wave. Now, well, here's something interesting, right? Sig equals sig times a new array. Let's do LF pulse 5 for index 0 and syn_osc.kr 0.5 dot range 0 to 1. All right, so now we have an array of sound generators, syn_osc in the left, pink noise in the right, and this array is being multiplied by another array containing 2 things. LF pulse .kr 5, so this is going to be an on-off pulsation 5 times a second, and syn_osc 0.5. So how does it handle this? Well, we have an array containing 2 things and an array containing 2 things. So this one is multiplied by this. So the syn_osc in the left is going to pulse 5 times a second, and pink noise is going to be modulated by this slower sinusoidal modulation. So it's going to be like waves crashing on the beast, you know, shh. So let's play it, and let's also look at the level meters. Okay, and the very best part about multi-channel expansion is that you don't actually have to create an array and fill it with thing after thing after thing. You can simply provide an array for one of the arguments, and then this is why it's called multi-channel expansion. The array expands outward and becomes an array of unit generators instead of an array of arguments. Let's take a look. syn_osc.ar. Instead of a single value, we're going to do 400 and 700 in an array. And we'll say 0, 0.2. So when we play this, it looks like we're providing an array of 2 values for the frequency of syn_osc. And so, you know, what does that mean? Which one is it? It can't have 2 frequencies simultaneously. Well, multi-channel expansion occurs. And let's just play it first. And it doesn't look like anything special on the level meters, but especially if you're listening on headphones, you can tell you've got a low tone in the left and a higher tone in the right. So basically, this line here is equivalent to doing this. Let's space it out. Sorry, there we go. Yeah. Now this is, you know, more stuff to type, right? So we could make the array ourselves and say, okay, first thing we want a syn_osc, 400 hertz, then we want another one, 700 hertz. We don't actually have to do that. We can just do this line right here. And this right here, this to this is multi-channel expansion. And remember, you can also do something like this, right? Exp rand 500 to 1000 exclam, oh, sorry, I forgot a parenthesis, exclam 2. Right, so remember, this line of code here, the highlighted stuff, generates an array containing uniquely generated random values. So now, every time we run this, we're going to have a different frequency in one ear, a different frequency in the other. And we could also provide an array here, so, you know, 0.2, 0.7. And again, if it encounters an array, 2 arrays, and it's trying to sort of, you know, reconcile those, if we have the array 400, 700 here, this line here is equivalent to, did I forget something here? Oh yeah, I don't want that. Don't need that. And this line here is equivalent to this, right? A syn_osc 400 hertz amplitude of 0.2 on the left, and sine OSC 700 hertz, 0.7 amplitude on the next channel in the right. So that's a very, scratching the surface intro to multi-channel expansion. I guess it doesn't get too much more complicated than that, but that's the basics of it. So the takeaway from this is that it is crazy easy to create a 100-channel signal if you wanted to. I mean, of course, normally you don't have that many outputs. I certainly never have, but I've had 8, and I've been to some festivals where you have like 64 or whatever, tons of outputs. And all you have to do is, a little bit of clever stuff with arrays and unit generators and maybe some randomness and some multi-channel expansion and the exclamation point. And it all fits together really nicely as a way to make like just 4 or 5 lines of code. And you've got this complex, evolving, modulating pink noise, sine wave, all sorts of interesting stuff. And, it's spread over tons of channels. So the last thing, I'm going to do one last thing. I know I keep saying that. I know it's 9:45. So, yeah, the cube. Yeah, Jake knows all about the cube. Okay, so if we look at the meters, you can see that the default, if you're using 3.8, is 2 in, 2 out. So if you're in a studio with 8 speakers, or you got an 8-channel interface with you and 8 loudspeakers, basically what happens is if we add another sine wave here, let's add some pink noise here, 0.1. All right, so now we have an array of 3 things, and I don't think this is going to feed back, but I'm just because of the way I have my audio hardware set up. Yeah. So you'll notice we don't hear any pink noise, and we don't see any pink noise, right? We just have sine wave amplitude 0.2, amplitude 0.7. So if we actually want to make 8 channels of something, the first thing we need to do is or server.local.options.num output bus channels. I know it's kind of a long line of code. Remember, you can just do s instead of server.local, and you want to set this equal to the number of hardware channels that you want to use. So I'm going to set that equal to 8, and then we need to reboot the server. So currently, oh, it already happened. Look at that. I thought you had to reboot. I'm going to reboot anyway. So we reboot the server, and then s.meter, and voila. Now we have 8 output channels. So we still won't be able to hear it because, I guess internet streaming is not, able to convey 8 channels. Plus, you're probably listening on headphones, which only have 1-2 cups. So, but we'll still be able to see it. So let's go ahead and do that. So just to tidy things up here, I'm going to do a semi-complex example that those of you who wish can sort of unpack it a little bit. So we're going to do sig equals pink noise dot AR. But first we're going to do amp. Amp equals, so this is going to be our amplitude modulator, right? Amp. So if we were to do just 0.1 exclam 8, there we go. 8 channels of pink noise. Of course, you're only hearing 2, but you can see that we've got 8 channels of pink noise right there. So let's change this to amp, and this will look kind of cool. Amp equals assign osc.kr, but this is going to have a frequency equal to the array 0.1, 0.2, ... 0.8. So this little internal parenthetical enclosure creates the array 0.1, 0.2, 0.3, 0.4. So we're going to have an array of 8 sine oscs running at these 8 different frequencies. So the one on the left is going to have a 10-second cycle, and this one is going to have what is 1 over 0.8? A 1.25 second cycle. And we're going to range all of these from 0 to 1. All right? And this is all we need to make this kind of cool looking thing. So we're going to have, so we have this array of 8 sine waves. And then as we plug it in to pink noise, this multi-channel expansion propagates through the UGen function. And pink noise then becomes an array of 8 pink noises with the amplitudes, or with these values from the sine-osc array, the actual sine-oscs themselves assigned to each channel. So let's just play it. Maybe I'll turn it down a little bit. How about that? 0.2, 0.15. There we go. Actually, you know what? I realized it doesn't look that cool with the noise because it's moving around so much because it's random noise. So let's change this to sine-osc.ar 0.1, and we'll provide a frequency of 300 phase and then the amplitude. So this should look kind of cool. Right, here we go. Right, so a full cycle later, and they are back in phase, right? And then they go about modulating the amplitude of the second sine wave at all different frequencies, but then they all line back up, and then they do it again. And so we're just hearing channels 0 and 1. But if I had a, you know, an 8-channel interface and 8 speakers, these would all be assigned in numerical order to all these channels. And you know, you can even go crazy. You can say, I want 16 buses, I want 100 buses. I mean, there's a limit, obviously. You know, you can't just make an infinite number of audio hardware buses. At least not today, anyway. So, right, that's the essence of arrays on the server and multi-channel expansion. You know, you could replace this with something that generates 8 random values, and you could also replace this with something that generates 8 random frequencies, so all 8 channels would be different frequencies. I could go on and on, but I'm going to close it here for now, because I've been talking for about an hour and 50 minutes, and I'm having fun. I can do this all day. Well, maybe not. No, maybe I could. But that's all for lecture, or online lecture week 2 for SuperCollider. So I would like all my students, I think I sent an announcement about this, but I would like you to watch my tutorial videos, particularly 4 and 5. Ultimately, I do want you to watch 3, 4, 5, and 6, but 3 has to do with synth and synth def, which we haven't really gotten to yet. We've just been doing function.play. And no problem, Pierre. So synth def is sort of like, it's when you graduate from function.play and you go to synth def and synth. That's like sort of, you know, that's, you're classier now, basically. A function, there's nothing wrong with function.play. It's just, it's like sort of it's very much a convenience to make sound. It's, let me turn that sine wave off. It's kind of soothing. I like that sine wave. Okay, so synth and synth def is something we'll get to definitely next week. We're also going to talk about conditional logic and iteration next week, and then we'll throw in some new unit generators, like maybe filters or something, as we have time. So yeah, please watch tutorials 4 and 5. Those cover envelopes and doneAction, and 5 covers multi-channel expansion. 3 is synth and synth def, and 6 is iteration, which is super fun, super handy, kind of a deep and complex topic, though, if you've never seen it before, but it's really efficient, and it just gives you tons more options with synthesis. So, right, if does anyone have any pastebin code they want me to look at? Has anyone been following along and stuck on something, or have any additional questions? If so, I'm absolutely happy to take those and hang around. I hope this was good. I know we covered a lot of stuff and covered it kind of fast, but you know, this will be up on YouTube tonight, and you can watch and you can skip through and yeah, just watch however many times you need, or all that sort of stuff. But yeah, questions are welcome. I'll stick around for 10 minutes or so, or however long I need. And thank you everyone for watching. Yeah, control rate and audio rate. Okay. I will put that in here just for posterity, because you can always skip to the end of the video, because I did have a little example prepared for audio rate and control rate. So in the help file for UGen, it mentions that all UGens respond to one or more of the following class methods: AR, KR, and IR. AR means a unit generator is producing samples at the sampling rate, which by default is 44,100 samples per second. And here's my understanding of KR. Every time I save a new file, my code devaluates. Do you mean evaluates? Save a new file, my code. Not sure what you mean. Okay, but KR means a UGen runs at the control rate. And the way software processes save as text edits. Okay, so when you save a file with Shift-Command-S, I would suggest making sure after you pick the location you want, go down here to the bottom and click this drop-down and make sure you save it as a .scd. Save as so like it saves as an RTF file or something like that. Yeah, just make sure you're doing save as. And when you choose save as, just save it as an SCD, no problem. Okay, so control rate is different from the audio rate. Control rate means the UGen is running at the control rate. And what is the control rate? The way software processes audio samples is in blocks of samples. So it doesn't, the program is not computing each sample one after the other 44,100 times per second, because that's kind of inefficient. It's the poor, I mean, it can do it, but if you were to do that, you'd see the CPU just be on average a lot higher, because it's more work for the computer to deal with that many samples. So instead it processes in blocks of samples. And the default block size is, s.options.block size is 64, which means one block of samples consists of 64 samples. Yeah, it would be a lot of interrupts. So this means that anything running at the control rate outputs one sample per every block, or per every 64 audio samples. So it's 1/64 the number of output values to create its waveform. And okay, I have an example here, which I'm going to copy here. So let's take a look at lfpulse.ar 50 hertz. We're going to plot this over 0.035 seconds, and I'm going to set the min val to minus 0.1 and the max val to 1.1. And this is just so that we can see the full pulse wave, because if we don't specify the min val and max val, the bottom and top of the pulse wave is going to coincide with the top of the graph, and it's just hard to see what's going on. And yeah, okay, so that's one of them. That's the audio rate pulse wave. And I'm going to plot a KR, and that's this one. And notice how they look different, right? Top one, AR, bottom one, KR. So I'm going to plot these with, what is the, I forget the, oops, the wrong thing. Find plines, it's plot mode. We're going to change the mode of this plot to be plines, which is points and lines. I don't think it works for audio rate, but it will work for the control rate. So let's just window.close all. And we'll just run this again. All right. So here's our, oh, I have to do an underscore here. Okay. So I hope this is big enough to see, but what we've got here on the top is a pulse wave at the audio rate and a pulse wave at the control rate. So these little circles on the control rate pulse wave represent control blocks. And so inside one of these segments is actually 64 audio samples. And so what we would see up here, if audio rate plotted with these points, is you would see 64 individual points in the space of one down here, and then another 64 and 64. So this actually has 64 times as many values as this one. And as you can see, there's no value in between this control cycle and that control cycle for the control rate, LF pulse. This one has no problem, right? It's just going along with the sample rate, and at the right moment, when its frequency dictates that it must switch from 1 down to the 0 section of the pulse, it turns on a dime, And so there's one sample right here, and the very next sample all the way down here, right? So it's just instantaneous change, instantaneous change. Now this one takes a little bit longer. Now it's running at the control rate, but if we multiply this by some audio rate unit generator, like as an amplitude modulator, the audio rate signal does have samples in here, and so SuperCollider needs to know how to do that multiplication in between this control block and that control block. And so what it does simply is linearly interpolates between them. So I'm going to change this code a little bit. And so we're going to do LF pulse times sinosc.ar 517 hertz. I've prepared this, obviously. I'm not just making these numbers up. So I'm going to just separate this so it's a little bit easier to read. So now we're not just going to be plotting the pulse wave. We're going to be plotting the pulse wave times an audio rate sine wave in both cases. So let's just go ahead and do that. Oh, I need to change the min val and max val. We're going to make this, because sine wave is bipolar. It goes all the way down to -1. Okay. Let's put these in the same order. So on the top, I have my audio rate pulse wave as a modulator. So it's on, sine wave has full amplitude, and then from one sample to the next, all of a sudden, the sine wave gets multiplied by 0, and it is 0 for that duration of that section of the pulse wave. And then suddenly, within one sample, it's back on again, right? And now, when we're dealing with a control rate pulse wave, at one control cycle has a value of 1, and then 64 samples later, it has a value of 0. So in the interim period, during those 64 samples, SuperCollider linearly interpolates between those two values in order to provide values that for this sine wave. It needs to multiply by the audio rate samples in the sine wave. And so that's why we have this very, very small fade out here, and then a fade in back here again. And so if we were to play this, we would hear, like, 4 clicks per second or something, click, 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 click. It would just, every time the pulse switches on and off, it's very likely that it'll just cut through one of these peaks or one of these valleys, and that creates a little click. But if we use a control rate pulse wave, it's running more slowly, and it has these, these little ramps. So anyway, that's one way to sort of visualize the control rate and audio rate. There are other ways to do it. One thing to keep in mind is that, like, for example, if we say sinosc.ar, let's do 400, and we'll just plot 100th of a second. We get this. And I haven't tested this, but I think if we change this to KR, this is basically, this frequency is really quite fast compared to the control rate, which is 44,100 divided by 64, which is 689. Let's go a little bit higher. Let's do 650 and 650. Okay, so I'm going to close these, and we're just going to plot these again. Oh, they're both audio rate. My mistake. Close these. I meant to make one of these control rate. So we're going to do KR. Yeah, okay. So what's happening here is aliasing, ultimately. Right? This is an audio rate sine wave, and it's got 44,100 samples per second. And at a frequency of 650, that's no problem. Here, the sampling rate for a control rate unit generator is essentially 689, and this is, yeah, right. It's just a really, really slow sine wave. So it's just taking the first value, it's imagine sampling this sine wave every 64 cycles. You might be here, and then maybe here, and then maybe here, and then maybe here. So this is an example of aliasing. So something running at the control rate can only go so fast without aliasing and completely losing its shape, because there just aren't enough samples. There aren't enough control blocks per second to accurately represent this wave. Now, if we slowed these down to like 50 and 50, this is probably going to be okay. maybe. It's closer, right? It's a slower sine wave, so we can get away with fewer points. But it's still, you know, this crummy sort of linearly interpolated garbage sine wave. So that's the control rate, right? It's just fewer samples per second. One sample for every 64 audio samples. Yeah. Okay. All right. I imagine a lot of my students have just signed off. They're like, man, this guy just keeps talking. And they're right. So I think now's a good time to call it, unless there are any last minute questions. So yeah, thank you everyone for watching. This has been week 2. Next week we'll do synth and synth def, conditional logic, iteration, and then possibly we'll start introducing some other UGens to make sound a lot more interesting, because we've just been doing Synosc, pink noise, whatever. So, okay, this was fun. I hope everybody enjoyed the stream, got something out of it, and I will see everyone. I'll see my students tomorrow in class with an in-class problem set, and I'll see everybody else next week, 8 p.m. Central. Yeah, thanks Kramer. Thanks again for the host. And all right, I'm signing off. S.quit. Let's get out of here. You're welcome, Graham. Thanks for watching. See everybody soon. Take it easy.